Greetings! We're going to be looking at carboxylic acid derivatives as electrophiles. Neat. First, we're going to take a look at the generic reaction. Then we'll be looking at 5 specific examples and the products they would afford us. So let's meet the stars of our generic mechanism. First, well, we need a carboxylic acid derivative. So we have a generic R group, we have a carbonyl, and then we're going to need to attach our leaving group. So our leaving group is going to determine what type of carboxylic acid derivative this is, if it's, for example, an ester or an acid chloride, etc. But we'll take a more specific look in just a moment. So this is character number 1. Character number 2 is our nucleophile. And I'm going to draw a hydrogen on a nucleophile because all the examples we're going to look at are going to end with a proton transfer at the end. So let's just add a hydrogen to this. And just so you know, the examples that we'll be looking at, we're either going to be looking at alcohol as a nucleophile, or an amine as a nucleophile, or at hydroxide as a nucleophile. Regardless, they all have a proton that's going to end up getting transferred at the end. So what is our generic mechanism? Well, our nucleophile is going to attack our carbonyl carbon. And as it's getting attacked, these electrons are going to withdraw up here onto our oxygen. We'll move that for convenience sake. So what's that going to get us? Some sort of tetrahedral intermediate. And I just want to quickly point out that here, I'm just assuming in this particular case that our nucleophile was neutrally charged. As long as that's the case, on that atom that did the nucleophilic attack will now be a positive formal charge. If this was hydroxide as a nucleophile, however, it would be neutral. So just to point that out really quickly. And the next step is going to be our pi electron striking back and reforming the carbonyl, and our leaving group, well, appropriately enough, leaving. So now we've got almost our products. Our leaving group has left. The final step is going to be a proton transfer. It's either going to be at the hands of the leaving group that left, or in the case of an acid chloride reacting with an amine, the amine will be a better base than the chloride leaving group. So, regardless, the last step is a proton transfer. So, whatever is going to act as our base is going to grab onto that proton, and these electrons are going to jump down onto the atom that the hydrogen was attached to give us our final products. Voila! So there is our generic reaction. And again, it comes down to 3 key steps. First is the attack on the carbonyl, and the electrons jumping up onto the oxygen. Next, we have the electrons from the oxygen collapsing back in to form the carbonyl again, and the leaving group leaving. And then finally, we have a proton transfer reaction that takes place to give us our more stable products. So let's look at a few specific examples and predicting the products based off of this. Okay, so for this first one, we have an acid anhydride reacting with an alcohol. So really, as long as we can picture the new bond that's going to be formed and what's going to be kicked off, predicting the products is pretty straightforward here. So first, let's just circle the leaving group. Our leaving group is just whatever's attached to the carbonyl carbon down here. Okay, and then next, let's picture the nucleophilic attack that's going to occur. So it's going to go something like this. Okay, so our products are going to be our carbonyl here, except now it's going to be attached to the oxygen from the alcohol. So we'll just draw in the rest of that. And our leaving group, but remember it's taking a proton with it. So we end up with an ester right here and a carboxylic acid for this particular reaction. For this next reaction, we have an acid anhydride and an amine. Very, very, very similar reaction, except now the amine is our nucleophile. So once again, our leaving group is going to be this fellow right here, and then we just need to picture what our nucleophilic attack is going to look like. So this time we're going to be forming a nitrogen-carbon bond at the carbonyl. So that means that our product is going to be an amide, strikingly similar to our previous product, except because we used an alcohol in the previous reaction, we ended up with an ester, whereas now, since we reacted with an amine as a nitrogen, we have an amide. And since our leaving group was the same, we're also going to end up with our carboxylic acid. Okay, 2 reactions down, 3 more to go. Let's have a look. So first, identify our leaving group. In this case, because we have a carboxylic acid, the OH minus is going to be our leaving group. Sort of. I say sort of because this is Fischer Esterification. You'll notice that we need sulfuric acid or some form of acid to help this reaction along. Hydroxide in and of itself is not a good leaving group, so we're going to need something to kind of coerce the reaction. That being said, predicting the products is done the exact same way, it's just there's some extra proton transfers involved in the reaction mechanism. Next, picture the bond that's going to form. It's going to form between this oxygen and this carbonyl, and then our products can be predicted from there. So we'll get an ester product, ergo Latin, the name Fischer Esterification, and our leaving group is hydroxide with an extra hydrogen on it, also known as water. Now you'll note this is not an organic product, this is just the water, but just to balance things out, we're going to show that it broke off here. Up next, we have this functional group here, which is an acid chloride, one of the most reactive of the carboxylic acid derivatives, because the leaving group, chloride, is a very, 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 very weak base. So, once again, we're going to predict the reaction that occurs. Actually, I'm going to call a mulligan here because while this reaction that we had written out would work, the reaction that we specifically look at in Chem 202 is that of an acid chloride with an amine. So I'm just going to change this to be an amine. Sorry about that. So anywho, same idea, just going to be a different product. If we would have reacted the acid chloride with an alcohol, we would have gotten an ester, but now we're going to end up getting, that's right, an amide. So we're going to have this tack in. Oftentimes when this reaction is run, you'll note that it's done with 2 equivalents of the base. That's because, or of the amine, well, both. That's because an amine is a much better base to facilitate the deprotonation at the end than chloride. So our products here are going to look like this. We're going to get our amide, and then we're going to end up with a salt, an ammonium salt with our chloride leaving group. Okay, and I'm just going to move these up here so that we can avoid the watermark on our last reaction. So this last one, we have this really, really long fatty ester. So we're reacting our ester right here with sodium hydroxide. This process is also known as saponification, and it's how we make soap. So let's see what we end up getting. In this reaction, hydroxide acts as a nucleophile and attacks our carbonyl. And our leaving group is this alkoxy group. So, what do our products end up looking like? Let's see, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 carbons in a row from our fatty chain methyl ester. Then we've got our carbonyl that will plop in there. And then finally, we've got the oxygen from the hydroxide. But remember, it's going to lose its hydrogen, just like all of our other nucleophiles in these reactions. So this is going to have a negative charge on it. So this is a carboxylate. And that negative charge is just going to be counterbalanced by that sodium that came from the sodium hydroxide. Okay, so we're going to have that. And then what of our leaving group? Well, it's basically the same exact leaving group, but like our other leaving groups, it's taking a proton with it. So we have our alcohol. So we'll just put that off there. It's kind of in the corner here. Maybe we'll move this. We'll make the hand from the watermark hold it. There we go. Great. Okay. And thus concludes this video on the generic reactions where carboxylic acid derivatives are used as electrophiles. And here are 5 specific examples of those and the products that we would get from these reactions. Thank you very much for watching. Have an awesome day.